The next thing we're going to talk about for this lecture is bringing together major and minor losses to do pipe flow, pipes in series types of calculations. Now, what we have is, of course, our typical reservoir system, but instead of having one pipe of one diameter going from reservoir A to reservoir B, we now have a pipe that has some other stuff going on. So if we think about the major losses, certainly we have the friction losses in both of these pipes, but now we've got two different diameters. One is bigger, and then we have a contraction, right? So two different velocities, two different Darcy-Weisbachs, right? At the same time, we also have these minor losses now that we're thinking about. We'll have an entrance loss. Here's a valve, so that'll have a minor loss as the flow goes through the valve, contraction, and then an exit loss. So we'll set this problem up just to talk about it, and then we'll solve it. But I also want to look at the energy and hydraulic grade lines between these two systems. And we're going to evaluate those and kind of draw them so that we can think about the energy losses as we move through the system. Here's all the points where we're going to think about what the energy is. So we'll have point 1 before the water enters the pipes, point 2 right after that initial head loss from the entrance. We'll have 3, we'll have a little bit of head loss between 2 and 3 from the major losses. And then we go through that valve and we'll have the minor loss at 4. We'll have some more major losses until we get to point 5. We'll have the minor loss through the contraction. And then we'll have major losses from 6 to 7, and then one more minor loss from 7 to 8 until we get to this next reservoir. So here is where we expect to have drops or changes in the energy as water moves through. And since we'll say the hydraulic grade line is equal to 0 at this point, right? We only have just the or not equal to 0, but equal to the water surface elevation. We'll say this is our datum. So the water surface elevation at the downstream reservoir will be our datum, and we'll start there, and we'll move up. So we can kind of draw this relatively speaking. So we just draw some sort of curve here. The energy grade line will start just below the water level, and it'll have a slope that's going to be less in the large pipe than it is in the small pipe. So take a second to think about that, why that is. Why is the slope of the energy or hydraulic grade line going to be more mild in the larger diameter pipe? Well, we know that from Darcy-Weisbach that it's proportional to V squared over 2G. So the hydraulic, or sorry, the energy loss from major losses from friction are going to occur at a lower rate for larger diameter pipe because the velocity is less. So the slope is related just to the major loss energy loss. We do this initial drop here because we have to account for the energy loss from point 1 to point 2. So we have that minor loss. Here's where our energy grade line and hydraulic grade line starts at the reservoir water surface elevation. We got a drop at the entrance, and then we have this mild slope until we get to this valve. Now we get another abrupt drop across that valve. We don't know what that value is, but we know it drops from that minor loss. And we maintain the same slope as before because we have the same discharge rate and the same diameter. Now, once we get to this point, we know we're going to have another drop. So we'll have another drop across this contraction. And now we'll parallel the hydraulic grade line here. So the energy grade line and hydraulic grade line always parallel each other simply because the difference is V squared over 2G. And velocity is always going to be the same in a certain pipe diameter. You'll notice that there's a gap here, right? And so this drop in the energy grade line is related simply to the energy loss across this expansion, this outlet here. Now we can draw the hydraulic grade line as parallel to the energy grade line above. And you'll notice that the separation between the two is going to be smaller. Let's take a second to think why that is. Why is the difference between the energy and hydraulic grade line smaller here than it is here for these two different pipes? Well, just like we noted before, the velocity is greater here, right? The energy loss is going to be more dramatic or a greater per unit length because the velocity is greater, right? And so head loss is related to velocity. Well, the velocity head is also related to velocity, right? So v squared over 2g is a smaller value here. This is a lower velocity. And here v squared over 2g is bigger. So that's the only difference, is the velocity between these two. Now we can add vertical lines just to connect everything. And we have at least conceptually drawn the two lines representing total head and hydraulic or static head across this pipe system, where we have these kind of dramatic drops across these different transitions. So now let's do an example where we actually calculate the head loss, accounting for major and minor losses. So let's take a look at this system. We've got the following: a pipe with a certain diameter, right? We've got a reservoir. We know the difference in elevation between the two. Got another pipe with another diameter, the same length. We're going to have, they're going to give us some information. So we say we're dealing with some cast iron pipes. All right. And we are given a flow rate between the two reservoirs. So Q is equal to 0.5 cubic meters per second. So we know off the bat, because we have a flow rate, we're just dealing with a type 1 problem. Now, we could do a type 2 problem where we say, here's the elevation difference. Go ahead and tell me what the flow rate is. That's when you get into double iteration. When you iterate for this pipe, you iterate for this pipe. It's a nightmare. I think you can imagine how to do it, and I'm not going to make your eyes glaze over too much to try to do that. So we're going to do a basic type 1 where we're given the flow rate and we want to find the total head loss between the two. So in this case, we're going to erase this and we're going to say we don't know what the head loss is. All right, so we want to find HF. And we can call this delta Z is equal to HF, because if we evaluate our energy equation from point A to point B, we know that the total difference in energy is going to be our head loss, is going to be delta Z. All right, so here's our setup, and we can go ahead and write our energy equation out. But first, let's just talk about what the different energy losses we'll have in this system. So we'll have an entrance loss. So we'll have a K-ents, we'll have a K valve. There's a valve right here. Then we'll have a, this is a sudden constriction. So as the flow reduces, and then we'll finally have a K exit. So these are our minor losses. We'll have 4 of them. And then we'll also have the major losses in the 2 pipes from friction. Let's write our energy equation. We're just going to evaluate it at the top of the water. So that'll be, we'll say PA over gamma plus VA squared over 2G. plus ZA is equal to PB over gamma plus VB squared over 2G plus ZB plus head loss. So off the bat, because we're doing the surface of the water, we'll cross our pressure and velocity terms, and then we end up with the relatively simple equation delta Z is equal to head loss. And so that's what we want to find is delta Z. And so let's unpack that head loss. So head loss is going to be equal to our major losses in pipe 1. And that'll be F L over D V, we'll say pipe 1, so V1 squared over 2G. And then we'll do our different minor losses. So that'll be K entrance plus K valve, V1 squared over 2G, plus whatever the sudden constriction is. So we'll look at that constriction minor loss. And then we'll also do the major loss. So we'll call that F1, L1, D1. So F2, L2, D2. So now we're looking at pipe 2. Velocity in pipe 2 squared over 2G. We know that'll be different. And then we also have this minor loss. So K exit V2 squared over 2G. All right, so we got a lot more terms to deal with in this neck of the woods, right? But we'll keep track of it. It'll be okay. Let's take a look at how we're going to calculate our minor losses. Well, if we go to our book, we can find that pipe entrance, they just use a standard value of 0.5 for sharp edge entrances. That's what we'll assume. If we look at the exits, we know that K is equal to 1. So K exit is equal to 1 for this kind of pipe exit situation. Let's look at our sudden contraction. Actually, let's look at the valve. There we go. For a valve, we'll assume it's a gate valve. If the gate valve is fully open, then we can use a K of 0.15, and we simply note it as K times V squared over 2G. All right, no big deal. And then let's go to our sudden contraction. This one's a little more complicated. All right, and this is just out of your book. For the sudden contraction, I'm going to be multiplying it by V2 squared over 2G. So it's the downstream velocity. And I need to find this coefficient. It's going to be the ratio of the diameters. So let's look at our two diameters again. We had 0.4 and 0.6. And so D2 was 0.4 and D1 was 0.6 meters. And so if we get that ratio, we'll do 0.4 over 0.6, and that's equal to 0.67. So let's figure out where we are. We need the velocity in the smaller pipe. All right, let's do that real quick. So we said Q is equal to 0.5 cubic meters per second. And we can then calculate our V1 by dividing Q over A1, right? And so I'll let you do that if you like, but you end up with 1.77 meters per second. And V2 is equal to 3.98. Okay. So velocity in the smaller pipe is somewhere between 3 and 6, right? It's 4. So we're going to be somewhere in this area, and then our ratio is 0.67. So it's going to be somewhere between 6 and 7 and 3 and 6. All right. So we could do an actual linear interpolation and come up with a number, but for our intents and purposes, we are going to just use a value of about 0.21, 0.21. So that's a little bit closer to 0.7, right? 0.67 is a little closer to 0.7, and it's a little bit bigger than our values here. So it's anyway. We'll run with it here. So 0.21 is gonna be our KC for contraction. Not the most user-friendly table, but you get the idea. All right, so let's go back to our problem. And we said that we basically just need to find all these terms. Because we're given velocity, then everything should be able to be solved directly. All right, so we'll remind ourselves that V1 was equal to 1.77 meters per second. V2 is equal to 3.98 meters per second. We can do our Reynolds number, 1, and we'll do V1 D1 over nu. Nu is going to stay the same. And they gave us the water is 10 degrees Celsius. So that means our nu is 1.31 times 10 to the negative 6. So we get about 8 times 10 to the 5th. Reynolds number 2 ends up being 1 times 10 to the 6th. So we can go to Moody diagram, and I encourage you to do that just for practice. Or you can do Swami Jane, and you can end up with, based on, can't forget U over D. So they gave us a cast iron pipe, so that is 0.26 millimeters. And we'll divide that by our diameter in millimeters, which is 600 millimeters or 0.6 meters. And that gives us 0.00043. You get another E over D right there with a smaller diameter pipe. All right, so we can take this with a Reynolds, go to Moody, and calculate F1, 0.017, F2, 0.018. And now we're getting pretty close. Let's go back up here and take a look at what we got. F1, L1, D1, V1, K entrance, K valve. We have the constriction, which is a function of V squared over 2G, and K exit. So let's go ahead and rewrite that just to simplify it a little bit. Delta Z is equal to our head loss is equal to K entrance plus K valve plus F1L over D1 all times V1 squared over 2G. double check. Yeah, it looks good. And then that's for pipe 1. And then for pipe 2, we have our contraction plus our exit times V2 squared. Oh, I forgot something. Major loss. And let's just do it in order, right? F2 L2 over D2 plus our exit. All right, now we kind of brought all the like terms together, and then we can plug everything in. K entrance was 0.5, K valve was 0.15. Our pipe length was 400 meters. Let's double check. 300 meters. Our velocity is 1.77. And then we'll do the pipe 2 major and minor losses. We determined that sudden constriction coefficient was about 0.21. And then our exit coefficient was 1 times velocity to 3.98. So we'll do all this math, we'll add everything together. All right, and so we'll just calculate these out individually. Note that I forgot to square the velocity terms. So good catch, whoever saw that. Don't forget to square velocity. So if we add everything up, multiply it by v squared over 2g, for pipe 1, I get about 1.46 meters of head loss, and for pipe 2, 11.87. So if I add those two together, we end up with delta z, which is equal to our head loss, should equal about 13.3 meters. So now we can go back up and say delta z is equal to 13. All right, and we'll get that entrance one out of there. Good job.